It's my pleasure to welcome Logan Beal as our speaker for this CAST webinar. He's going to be joining ExxonMobil this next year as an application engineer. Currently, he is a PhD candidate at Brigham Young University. In my group, the Process Research Intelligent Systems Modeling group, his research interests are in the areas of nonlinear predictive control, nonlinear programming, solver development, process simulation, real-time numerical methods, and moving horizon estimation. He led the development of the combined scheduling and control proposal and also the fulfillment of that in the NSF Eager project called Cyber Manufacturing with Multi-Echelon Control and Scheduling. And so with that introduction, I'll go ahead and turn it over to Logan now. So Logan, welcome.
Thanks. Today I'd like to talk about GEKKO Optimization Suite, especially sharing a bunch of code samples and walking through what GEKKO can do, what sets it apart. So I've prepared the code that I'll be walking through today. I've put it in a Git repository, which I've just shared in the chat window if anyone wants to look at the code and tinker with it while we're going through. GEKKO is unique because it was originally conceived as an industrial solution for closed-loop control and estimation problems, and over the last few years, it's been used for academic researchy purposes. So it's got some features that hit both areas. As a quick start guide, because it's a Python package, you can install it with just pip. Pip install GEKKO from the command line. It's really easy on Linux and Mac because of the command line integration. On Windows, I tend to use Anaconda. So the Anaconda prompt works for this command line. Just pip install GEKKO and you'll have it there in Python. There are also these 18 examples to get you started on GEKKO at that link there. So GEKKO is a free algebraic modeling language in Python. It solves linear programming, quadratic programming, nonlinear programming, mixed integer, linear, and nonlinear programming. So it is free for academic and commercial use. Have fun with it. Do whatever you want. We believe it's easy to install because it's that pip package and it has intuitive syntax. And we tried to integrate everything together in one package, model formulation, solution, and visualization. So it's a complete package, about as complete as it gets without being GUI driven. You can't be afraid of code, but we believe that provides some flexibility. Its specialization is in dynamic optimization. Like I said, it was designed, conceived for closed-loop control and estimation purposes, so it's fully featured for those applications, including some online tools for like measurements and measurement value validation. Also some time shifting solutions. So for every subsequent solution of a controller solve, it will shift the previous solution automatically for you, which provides the initial values for your differential equations, but also gives initialization for all the other values in the horizon, which makes the controllers a little bit more robust and a little bit more stable. It also has some model reduction and initialization strategies to help you get that robust solution. So first, why did we choose Python? I personally really like Python. I think it's easy, flexible, and pretty. It's also a very popular language. IEEE rated it #1. The TOB index has it at #4 right behind Java, C, and C++, and it's still climbing. That popularity brings a large community. Almost every time, whenever I have a question on Python, it's a quick Google search away and I know the answer in 20 seconds. And that also gives many powerful packages such as matplotlib for your plotting, NumPy and SciPy do all your numerical problems. Pandas gives nice data frame access, Excel, and then some packages like OpenOPC and PyModBus allow it to interact with real systems. And pip install is just great. I am an opponent of the one tool fits all. I don't think Excel should be used for everything, but if there were a universal tool, I'd say it's Python. So as an AML, it does the standard things. It solves that the problem here on the left, minimizing an objective with equality and inequality constraints. AMPLGAMS, PyOmoJump, Casati, and other modeling languages all address the same problem because this is what the solvers, the nonlinear optimizers on the back end, this is what they solve. So this is the core for everybody. That's nothing new. GEKKO uses automatic differentiation to provide exact first and second derivatives. And even though it's in Python, it drops into Fortran on the back end for faster function calls and integration with the solver. One unique thing with GEKKO is that it comes with the bundled solvers. Once you install GEKKO with pip, you've got the solvers available. IPOpt is the default solver, and it also features APOpt and BPOpt, which are custom active set and interior point solvers. Also available are Minos, SNOpt, and KNitro, but because those require licenses, we don't hand those out by default. But if you do have a license for those, we can get you GEKKO with those solvers bundled in and tightly integrated. Here's the first example of code. This is the HS71 test problem. It's very popular. So this code is available in that repository if you'd like to start tinkering and see if GEKKO works for you. So you can see here, let me pull up my laser pointer. So we import the package here. That's just Python syntax. We initialize a model. We set up our 4 variables with their initial value, lower and upper bounds. Here are the 2 equations with regular Python math syntax. Our 1 objective, we set the mode to steady state optimization because there's nothing dynamic in this problem. We solve it, and because we're all in Python, the results get loaded straight back into these variables we've created, and we can just print the values right there. So it's all right there, all in one piece. So dynamic optimization is kind of the specialty for GEKKO. That extends the regular algebraic problem to differential equations. Specifically, GEKKO is designed for just ordinary differential equations in time, and it has built-in discretization for that. Most modeling languages require you to provide your own discretization.
Has joined the meeting.
GEKKO will do automatic orthogonal collocation on finite elements. If you need PDEs, then you do still have to do your own manual discretization and space. And providing that discretization is just right here, giving time discretization, and those are the bounds on your finite elements. And you can set the number of nodes inside in a separate option. So it does have both simultaneous and sequential methods for differential equations. The sequential method means that the differential equation is solved separately from the rest of the optimization problem. So one is solved, the differential equation is solved, integrated, and then the optimization problem iterates sequentially. So this is kind of the easy one to implement. You can use your favorite differential equation integrator. One of the pros is that because your differential equations are being directly integrated, they will always be feasible, because as long as your differential equation integrator gives a solution, then even if the solver gives up halfway through and doesn't find a feasible solution, you know that your dynamics are still fairly reasonable. A simultaneous solution breaks down the differential equation, discretizes it for you, and solves that as part of the set of algebraic equations. So it's all solved together. It's more difficult to implement, so that's why we have it built into GEKKO, especially because there are sparsity patterns that arise. We can take advantage of that with all the sparsity structures and make it easier for the solver. That's why we've built it in there in the back end. It's difficult to implement if you just tried to do it yourself. It's not as easy as sequential. However, the downside to a simultaneous solution is that if the solver doesn't reach an optimal solution, it's very likely that your dynamics are totally wrong, because these algebraic equations are not guaranteed to be satisfied. I've been trapped in that a few times. When I reach a solution and throw out the plot, I say, wow, these dynamics are great. That controller got to the set point really fast. And then I realized it was just infeasible and the dynamics were totally wrong. And so I got trapped in that a couple times. So just know that if the solver didn't work, your results are no good for anything. Common implementations of dynamic optimization include model predictive control, moving horizon estimation,
has joined the meeting.
Dynamic real-time optimization, economic model predictive control. So these model predictive control and moving horizon estimation, we have some features built in to facilitate those modes, modes 5 and 6, which we'll look at here. We also have custom variable types that facilitate these dynamic optimization problems. The vocabulary is borrowed from the process control community. Manipulated variables, controlled variables, everyone recognizes. So a fixed variable is unique because it's fixed throughout the horizon. Whenever we do a dynamic mode, all the equations and variables are automatically discretized through all of time. You don't have to manually define your equation for every point in time. Pyomo does that. It provides some extra flexibility, which is their goal. We're going for simplicity. So everything just gets automatically discretized. If you need a fixed variable, you're estimating a parameter through time.
Has joined the meeting.
You can use these fixed variables. It has some built-in tuning, such as Dmax or a delta, a maximum delta, so the values can't change too much. That both provides some stability, helps your solver not search too far out in space, but also helps you remain physically consistent with your problem. Manipulated variables are like regular variables. So most of Gecko just uses parameters, constants, and variables. Those are kind of the default types, where variables are the degrees of freedom solved by the optimizers. Manipulated variables with the status on, here, this option, means that it's also a degree of freedom, but rather than being a degree of freedom at the finite element bounds and the nodes, they are zero order or first order hold, because when you have these advanced control systems, you typically implement these manipulated variables, you pass them down to your distributed control system, the DCS, and they typically don't follow a nice smooth polynomial inside the finite elements. They typically a zero or first order hold where it passes the set point to a PID controller. So these are set up to facilitate that kind of a structure. It also has tuning options like a cost on a delta decost, which is move suppression, just penalize movement. That'll smoothen things out, and again, a Dmax or constraint on how far it can move in each time step. These are great for model predictive control, but sometimes I find in my academic problems that aren't directly model predictive control that these tuning things will still help with the optimizer. So you can mix and match all of these special variable types into any problem type and just leverage these automatic equation writers. Dmax, because it's an absolute value, which is not continuous. We have special formulation where that makes it continuous, and it's a lot easier to just use the Dmax option than to write the continuous version of the absolute value. State variables are, I think, mostly just there for completeness sake, because you can already see the values of the variables, but it does add some extra attributes, like after you solve, you can see its predictive value, which is just the one value at the next time point. Controlled variables are, again, another powerful one, where they build objectives for you based on your mode. If you're in a control mode, then you just set a set point. For example, here you have X is a controlled variable. You turn it on, that means please build my objective for me. If the status is 0, then it's just a regular variable. And then you set your set point with squared error, or you can do an absolute value, and this is again the smooth version of the absolute value. Then you can do a set point high, set point low with a dead band in the middle with no penalty. just like that, it'll build your objective for you. There's also some tuning available on the CVs there. So there is MV and CV tuning available at the same time. For example, rather than just having a fixed set point, you can have a set point trajectory, which encourages kind of a smoother solution. And so you can set things like the tau, the time constant, on how quickly you want to reach that set point, or how smooth and slow it should be. Another unique variable type is intermediates. They're a form of model reduction because these equations are solved explicitly and directly rather than being solved implicitly in the matrix math. So, for example, if you had this Arrhenius expression, rather than finding k and then using k in your rate equation, k will be calculated directly and explicitly. This is mostly valuable when you have a very large problem. For example, you discretized a lot of points in time. Your problem gets big, and eventually the matrix math exceeds some hardware limitation and time just blows up. So by moving problems out of that matrix math and the implicit solve to these explicit solves, then it's just a flat linear time. They all just get solved. Their values and derivatives get propagated through as needed into the matrix math for the solver. One benefit is that these ensure feasible solutions of these equations. That's kind of like the benefit of a sequential mode versus simultaneous mode for differential equations, where you guarantee that these equations are solved, even if the optimizer returns infeasible in the end. So now we're going to look at a few examples and dig a little bit more into the code. So feel free to jump along, follow the code from the Git repository if you'd like. First, we're going to look at a CSTR model. We'll build the model. We'll look at how to do RTO, nonlinear model predictive control, and then tune that controller just briefly. So in this model of the CSTR, we're looking at concentration and temperature. Inside the reactor, it's just a first order A to B. Concentration is our controlled variable. That'll have a set point, and the temperature of the cooling jacket is our manipulated variable. So first, we'll just initialize it. We'll import some of our packages. We've got Gecko, we've got NumPy. That's handy to create our time discretization. We can just discretize, give us 51 points. Discretization of 0.1 from 0 to 5, and matplotlib will give us some plots at the end. So then we define all of our variable flow rates and volumes, densities, and heat capacities. These are all just fixed parameters. They could be constants as well. Then some of our variables here, and like I said, this is our manipulated variable. The cooling jacket temperature and concentrations are controlled variable. So we'll use those equations, those variables here in our equations. This is just 4 equations, 2 of which are differential. So this is how you'd set up a differential equation. Ca.dt will automatically discretize concentration in time. Same here with temperature. So as you can see, this is a nonlinear problem, but Gecko will solve it just fine. So here's everything all together. It's a little bit smaller, but it's not too many lines of code for model predictive control. So to set up real-time optimization, we'll set I-mode to 3, like we did with the HS71 problem. That means this is a steady-state optimization problem.
Has left the meeting.
These mode numbers are listed in the documentation. So in a steady-state optimization, it'll just set all of your differential equations or differentials to 0 and solve it just steady state for you. We've got our controlled variable type as a squared error. We're going to turn on our manipulated variable, turn on our controlled variable, so it'll build our objective for us, set the set point and solve it, and then we'll print those values. And this is the optimal steady state for a set point of 0.5, temperature of 350 and cooling temperature of about 300. So as we do the model predictive control, you can watch for that. The cooling jacket temperature should go to about 300. So by changing just this one value, I mode is now 6, that's dynamic optimization. We're now doing model predictive control on the same model. And here you see the results. Concentration goes to 0.5, and like RTO said, the cooling jacket temperature goes here to about 300. So now if we look at this, we could say, okay, we've done model predictive control. It looks like it works, and maybe we can say this is physically possible to swing your temperature this much in an hour, but let's say it's not so good. Someone's going to be upset that it's swinging too hard, it's not good for our equipment, so we want to tune that a little bit. So we don't need hard constraints, because we can we'll say it's physically possible. We just want to suppress the movement a little bit, and just make it a little bit smoother, a little bit slower, make everybody happy. So we'll add one line here, cooling temperature, decost. So penalize movement. The value of these decosts is where we start to reintroduce art into controller tuning. But you can gauge the value of the objective function from previous solutions and try to play in. This is the cost for each movement. So now we see that we've told the optimizer, don't move so much, be a little bit smoother. So now these cooling jacket temperatures don't swing nearly as far or nearly as fast. It's a lot smoother. And we can say that, yeah, that looks like the kind of control we want to have. Okay, so that was just a couple of changes. We went from RTO to NPC to tuned NPC. Next, we'll look at putting a model online. We're just going to look at a generic first order model. We're going to set up two separate models. One that will be our simulation, can represent our actual plant, and another one for control will show that we can do measurements, time shifting, control moves. They're all just built-in attributes of these of the objects. So here's a lot of code. I wanted to show complete code samples so you can get an idea of really how much code there is for two models. I think this isn't too bad. So here's one model. This is going to be our process. Here's our first order equation, a couple of parameters, one variable, time discretization of 0.5. So we've got to match our time discretizations here. Here's our controller model. Here's some controller tuning. And I've taken the process and just put it in the function that says simulate. We've got a real process. So you can note here that I've done some model mismatch to pretend like it's a little bit more real. The gain values are slightly different, and the tau values are slightly different. And I'm adding noise to the process.
Has left the meeting.
So once we've got those models, all we do is put it in a time loop. U is our controller manipulated value. We're going to send in the new value from the controller, simulate the process, and put the measurement back into our controller CV. That will give us a bias automatically. And every time we solve, it's going to time shift. It's going to use that bias. It's going to initialize the values in the future for a steady solution. And this is the result. So I've also changed the set point halfway through, just like that right there. So you can see that because of the noise and the model mismatch, it's a little bit jumpy here. It looks more like real life, less like an academic problem, even though it is. So in real life, we at BYU don't have big process equipment to test it on, but we do have this temperature control lab, which we've designed and used at a number of universities to pretend like we're doing some fancy real world thing. It's an Arduino with a couple of transistor heaters and a couple of thermistors, and we're just going to try to control the temperature. So in this particular case, we're gathering data. This is sped up, but live data. We're measuring our temperatures here. We've got measured and the predicted values. This is for moving horizon estimation. These are the parameters we're trying to measure, the gains and the time constants. And here are the measured heater values that are being used. So as you can see, as we go through time, these fixed variables start to steady out. That's a good use of fixed variables because these k's don't change in time, but we're trying to estimate them and getting better estimates through time. Now the same problem, we'll just switch to predictive control. This is again sped up. This is almost 1,000 seconds, or we're watching in 20 seconds. But that's multiple input, multiple output control. Could have maybe been tuned for a little bit more move suppression if you want, but keep in mind this is changes over hundreds of seconds, and it's just electronic heater, so not too bad. Another example that we could do is some hybrid neural networks. This is something we've been tinkering with since neural networks are the cat's pajamas these days. Everyone wants a neural network, and for problems like what Netflix show should I watch next, they are an excellent solution because you have tons of data and you don't really know how to model that. As engineers, we've spent many decades finding mathematical models to describe our systems, and so they're better than neural networks. However, we do find that occasionally there are parts of our model that we don't know how to describe so well, so we're exploring the use of neural networks inside our model, inside of a physics-based model, because neural networks have poor extrapolation outside of your data region, or if your neural network is too large, it even has poor interpolation if you've overfit. But if you can provide some physics-based equations to give it some structure, that will help with your interpolation and extrapolation, and you also need less data to get a decent fit. So we've been playing with this in Gecko. That's kind of an active research area, how to facilitate faster neural networks. One of the reasons Gecko is unique for this is that intermediates variable type, which is packages like TensorFlow, don't solve your variables implicitly. It does it explicitly, so we can kind of blend that in. We're not pretending to be any sort of replacement for TensorFlow. If you have a huge problem, parallelization of your derivatives on GPU is pretty impressive on TensorFlow. But if you'd like to mix it in with some constrained optimization, then Gecko, we believe, is a good package for that. We also have a GUI. This is our attempt at being complete package. This is one of the areas of active development, finding out exactly what people are looking for. It has two objectives. One, in an academic sense, when I write a little problem, a little test script, a little warm-up, sometimes writing the 10, 15 lines of matplotlib to show the figure takes as long as writing the whole model. So you can just pop open this GUI and it'll automatically load the variables and give it a nice plot. Or bigger solution is for if you actually have online control and estimation, then you can watch your solution as it runs. It has a client-server structure, so it just spins up a little microserver, and you can it will open up your browser and point it right there if you're doing a little academic problem, or if you've got Gecko running on a server somewhere, then the engineers can be watching the solution remotely on their own desktops.
Has left the meeting.
Here's back to that model predictive control sample problem that we did earlier. Just by running GUI equals true in our solve command, it'll open this up. You can see here on the right that it loads in all the variables we had. This uses Plotly, so it's nice and pretty. You just click what you want to plot here. This will show our concentration and our concentration set point and our expected manipulated variable changes. Also, here's that closed loop online with the first order models. When you solve it in a loop, it stores some of your recent data. Here's the controlled variable, here's the manipulated variable, here's what has happened, here's our expected moves of the manipulated variable and the anticipated trajectory for the controlled variable. You can see that it expects with this move, it should fall within the set point band. Just stop that one during that transition to a new set point. So this is kind of what we imagine engineers could use to watch their model predictive control online. We have a few extra features as well. These are kind of the things that we've brought back in from an academic perspective, a little bit more flexibility that we want to solve these new cutting edge problems. One of which is connections. Like I said earlier, the equations and variables are all discretized straight up for you. So you don't have point-by-point control for equations or fixing values. These connections reintroduce that control. So you can, for example, fix value and connect it to any point in a variable, and now you have control of just that one finite, or that one value somewhere in the horizon. So you can set extra constraints at a certain point, or fix a value somewhere in your horizon, or do periodic constraints. Optimal control problems are a good example of this because by definition they have some integrated objective over the horizon, and then they have some fixed objective at your endpoint. So if you need to meet your endpoint, so for example, this is just an integral. So we've swapped that integral for a derivative. Here, we've set this j is equal to the integral of this equation, and then we want to maximize just that at the final point. So we set this j final as a fixed value. We turn it on so it's a degree of freedom, and then we connect the final point to j at the end. And then we can maximize just that final profit. So that's just an example of getting a little bit more direct control of pieces of a discretized variable. There's the results for that problem. We can also do periodic constraints. That's a special case of connections where the end is fixed to the beginning. Here's just a sample made up problem for that. But you can see that the end is equal to the beginning there. We're also doing some pre-built model components. Doing this, building models in Python gives you a lot of flexibility. However, you are restricted to using these Python, the Gecko variables and special variable types, and some of the standard Python math, some trig functions, error function. We've overloaded as many of those functions as we can, but there are still some features like people frequently want if statements or other models that are not continuous. They just don't work with the gradient-based solvers. So we're trying to implement some of these models pre-built in the back end where we can directly modify the values and their derivatives, so we can pretend like these things are continuous or set them up specially to work in the solver. For example, we have some state space models, which continuous state space models we can just set up as a system of equations, but discrete state space models are not so continuous, or you can't really set them up in Gecko syntax. So we've got discrete state space splines. If you just hand in some data, Gecko will build splines for you. We're also looking at some of these other options like mathematical programming with complementarity constraints to approximate some of these discrete functions, adding in some thermodynamics or some flow sheets, adding in so you can just piece together some of these pieces of process equipment in your code or transfer functions, etc. So this is also an active area of development, but we do have some built in already. For example, here's a spline. Here's the boilerplate. This is the function I'm generating data for. Just generating some random data here. And then I pass in the X data and the Y data, and I link that to these Gecko variables, X and Y. And then I'm trying to find a minimum in my Y. Solve that, and here are the data points, and that's the minimum I found. So this is good for if you have a large simulator whose solutions take too long to be put into an actual optimization, but you've generated a set of points. Then you can just take that data, and you basically get an approximation with some interpolation that Gecko can do for you. This is a C-spline. We're almost done with B-splines, which are a little bit smoother. Should avoid some problems with local non-convexities because of noise and such. Here's a state space example. We've got our A, B, and C matrices. This is a linear state space model of a Boeing flying at 40,000 feet. And here you can see this is where we actually build the state space model, passing in those A, B, and C. This particular one is continuous time, but you could also do a discrete time state space model. And here's just some tuning where we're tuning that airplane to fly how we want, and these are the results. So here's that state space model, an airplane, and it works great. Here's some additional resources we have. The documentation is available on Read the Docs, the repository. We have a paper we just published in Processes, special issue about modeling, and there's a dynamic optimization course which Dr. Hengren teaches that uses Gecko. He'll start that up again in January, and you can join along with that and get some more hands-on experience on some problems along the way. So I'll take some questions now.
Okay, great, Logan. And I've been trying to answer some questions through the chat window as well. We'll just bring up those. One question that I wasn't able to get to in the chat window right away, but this would be good for you to cover is, are you able to index variables in this package?
Index them in setting up the equation?
Yeah, in terms of creating a variable that might be an array versus just a single value.
Oh, okay. So yes, with that, we just use Python syntax. You just create a Python array of variables. List comprehension makes that syntax pretty compact and smooth. So for example, we could say in the original HS71 problem, instead of saying we have 4 separate x values here, we could create an array x equals list of 4 variables, and then we just use that index x, x0, x1, x2, x3. So that you can do that because it's in Python. We just use the regular Python syntax for those types of arrays. If you're talking about indexing them through time, then that's where you use the connections to access them directly at specific points in time.
Great.
And then,
okay.
And then what? Okay.
So another question that came in: how do you introduce scaling factors for both states and inputs?
Scaling. A lot of solvers like IPOpt do some scaling for you. Gecko on the back end will also do some scaling for you. But if you really want it properly scaled, then you just scale the variables and the equations yourself, just manually.
Okay. Great. Does Gecko have algorithms for solving multi-objective functions? For example, dynamic optimization with multi-objective function with many objectives.
If you add multiple objectives, they will just be summed together to create one objective. So you can use the objective command multiple times. It will not automatically build a Pareto front for you. So you could just set up your solution in a loop and build your own Pareto front. But it is just a single objective solution.
Great. And I will add one other thing. There is a tier option that is available for certain MVs and CVs. So you can solve them in multiple phases, where you solve a certain, first tier, for example. Let's say you want to try to control properties for a reactor, and then as a next tier, then you want to increase production rate, but you don't want to use the MVs from the production rate to affect properties. So it has explicit decoupling that is available. Okay, let's see. Here's another question. I need to import a large data set into Gecko for an MHE dynamic optimization. Any hints on how this can be done?
Yeah, Gecko will read in your NumPy arrays. So pandas will also, if it's in a CSV or an Excel, pandas is pretty fancy for reading in that kind of stuff, and then it can output the values of the columns as NumPy arrays. So here, for example, where we set the value of x1 to 1, that's just an initial value, we could just set this as a whole array, and that would be, that array has to match your time discretization, but they just plop that in as an array right there. If you're solving it in a loop, then you'd pass it in as a measurement like we did with the controller. But if you're just doing a one-off estimation, then you just pull it in. You can make it a Python list or a NumPy array. You pop it in as a variable right there.
Okay, great. Well, we had another question about making your slides available. Can you post those to the GitHub repository?
Sure, I'll put them in there.
Okay, great. So for those who didn't get it initially, Logan posted a link. If you go all the way up to the top, there is a link for a GitHub repository, and it has all of the source code that Logan showed here in the presentation, and then we'll also, put the presentation is there as well. Okay, so let's see, I have another question. Are there problems or situations where you'd use APMonitor instead of Gecko?
If you want to use MATLAB.
Okay, so the MATLAB interface, the APMonitor, and then Gecko is like the latest version for Python. Okay, great. Okay, any other questions? We got a little bit more time. And you're welcome to unmute your microphone as well if you'd like to just ask a question or discuss with Logan. So I got another question for you, Logan. Actually, we just got a couple more, but let me give you one of the feeder ones that I was thinking about. What's next with Gecko?
We want to continue developing the GUI so it's good and robust for various applications. And then we're going to keep working on some of these built-in objects to provide some more flexibility. But I think it's an open source project, so if anybody wants to contribute or has any ideas, we'll take it wherever the community wants it.
Great.
Hi,
okay.
This is Jeff Cantor. Can you hear me? And can I ask a question?
Sure.
Just a quick question. If someone has to make the decision between Gecko and Pyomo, what decision criteria should they use?
Yeah, so I used Pyomo when I first started my graduate studies because I was doing combining scheduling and control, which was kind of a new area. I didn't really know how it was going to play out. So I thought the extra flexibility that Pyomo claims would be really helpful. And they are indeed quite flexible. So if you're really looking for that, your problem's got some weird structure, you've got some interesting sets. They do some interesting things with formulating some pieces of the puzzle for you. You're just looking for any sort of random flexibility, PDEs and such, then Pyomo's the place. If you have a problem that fits kind of a standard model predictive control, if you don't need super tight control over your horizon or multiple dimensions, then I believe Gecko is much easier. After spending some time in Pyomo and deciding how I wanted to structure my problem for combining scheduling and control, I found that it could be formulated in Gecko. I moved it back over to Gecko, and it was easier to set up and faster to solve. But it just so happened that it fit in kind of a model predictive control format. So.
Okay, great. That's really thanks.
What was the speed up you observed, Logan?
In that particular problem, which was quite large, it was about 5 times speed up between Pyomo and Gecko. That's I don't think that's a good representation of how the speedups you'll always find, but in that one case for the large problem,
Okay.
Gecko did significantly better.
Okay, this is Jeff Cantor again. So let me just ask a question on that last statement. When you say speed up, is that relative to the model formulation or to the whole model creation plus the numerical solution?
Yes.
All right.
the whole time. So I'm not exactly sure where all the speed up came from. Pyomo
Has left the meeting.
does a lot of the model building, including the discretization in Python, which is somewhat notoriously slow. They're not looking for speed. Gecko does the discretization in Fortran, builds all those matrices there. So the model compilation is more than 5 times faster. But even the time in IPOpt, the formulation has been modified just slightly. But I think there were some other things about how Gecko does some scaling, some of the tighter integration for the function calls, that even the time just spent in the solver was faster.
Great, thanks.
Hello, Logan. This is Ahmed. I was in the dynamic optimization course with Professor Hedegren. I'm actually would like to say thanks for this presentation. It was great as usual. The material is very well prepared, and I honestly have not touched the Gecko since the course finished, but I've been working on a state estimation problem for a vehicle dynamics utilizing like a multi-body degree of 3 degree of freedom vehicle model, and my interest here is I'm going to be utilizing Gecko for a moving horizon estimation to give me benchmark results that can be compared for the existing algorithm, which relies on the extended Kalman filter and so on. The reason I'm doing this is the Kalman filter, is pretty economic to implement in real time, at least for the needs of this project. But
Has left the meeting.
The moving horizon estimation has got the capability to, it's essentially an optimization problem which can deal with constrained variables and things like that the Kalman filter would not be able to. And that's why I asked the question about importing data into the moving horizon, importing the data needed for the moving horizon into Gecko.
Oh, yes. So if you'd like to simulate it as if it were in real time, then you would just solve it in a loop and pull in the data one at a time. We have some more information on how to set up moving horizon estimation, both in the dynamic optimization course. There's a sample problem in the original 18 here that we've provided there, and some more in the GitHub repository. There's some examples.
Excellent. Well, thank you so much for this. I really appreciate that.
Sure.
Great. And yeah, thanks for bringing that up again. I'll just paste this because sometimes it's hard to get it into your translate it from the screen into your web browser. So there's the list of 18 example problems if you'd like to run those. Okay, so I've got a whole list of questions. I'm just going to try to go through these pretty quick, Logan.
Okay.
So for example, by using Custody, we need to design NLP, but for Gecko, it is not needed. What is the optimal method behind it? So let me maybe rephrase that a little bit. Maybe in Custody, and I'm not incredibly familiar with Custody, but maybe there's a lot more. You showed the HS71 problem where you're just defining equations and variables and then you say solve. So in Custody, it sounds like there's a couple extra steps. So any comment on how you're translating that into a mode that the solver can handle?
Yeah, so I think that's these I modes. We'll just give some general structure. I've looked at Custody just briefly. It's another package kind of like Pyomo where you get some of the added flexibility, but you have to give it more instruction to allow for that flexibility to set up your problem. So I think it's these things like the I mode, where in Gecko you say this is steady state estimation, steady state simulation, dynamic control optimization. A lot of that just gets bundled right in there. But all of the solvers are nonlinear, so it's not like you have to specify a problem type to pick the right solver. It just treats it passes them all to a nonlinear solver, although you can define it as a linear problem with a model option, but we tend to use nonlinear problems.
I just put a link in there as well, just for orthogonal collocation, a little bit more of a tutorial on how differential and algebraic equations are translated to NLPs. So if you're interested in that. Okay, so on to the next question. Can he expand on model reduction and hybrid neural network modeling?
Yeah, that's two questions. So for the model reduction, there's just an option where you can tell Gecko to try to reduce the model, and it'll pick out some of the easy things in your model, take out some of the equations. That just helps you to write a more coherent model for humans, but it speeds it up a little bit for the solver. These intermediates, is the intermediates you're talking about for the model reduction? Those just, they shrink the size of the matrix math, but they don't always make your problem faster or easier. I've seen it go both ways. For a nonlinear problem, sometimes giving that implicit equation solved in the matrix math will slightly adjust the direction, and when these nonlinear, not quadratic problems, it can shift the search direction a little bit, and you just get lucky. Maybe it's a little bit better by having it in intermediates or not. So it's not guaranteed to make your problem faster or better, but it's a nice tool to have. However, in combining it with the neural networks, tools like TensorFlow, don't worry about implicitly solving all of your nodes and the activation functions and everything. That solves it all explicitly, and then does the back propagation, which is just a special case of automatic differentiation to get your derivatives. So we can combine that and enhance. I've tried neural networks with both intermediate,
has left the meeting.
Explicit solutions or implicit, and I found that the intermediates tend to solve much faster, but sometimes they get caught in maybe a worse local minima near your initialization, whereas by providing them the nodes as implicit equations, it gives the solver a little bit more freedom, and sometimes it wanders over to a better optima. But setting up a neural network inside your model is just setting up the equations for building the nodes and the activation functions, some summations and such. We plan on releasing a little bit of code to facilitate building such layers in a Gecko model, but just a little bit of search on how neural networks are set up. It's just a large nonlinear model. You can set those up yourself. Not too bad, especially with loops.
Okay, any recommendations on Python versions? Will it work in Python 3.6 or 3.7?
It should work it in all Python versions after 2.7, although 2.7 is reaching the end of life here within a year or two. So just go with the newest one. We'll keep it working for the latest Python.
Okay, great. Okay, we have one other question. Can Gecko handle multi-objective problems? Sorry if I missed that part. So I think that was covered earlier. So we'll post this as a YouTube recording. You can go back and listen to that later. Okay, any final questions that you have? Okay, great. Well, Logan, thanks a lot for your preparing this presentation, and a great job. Really great motivating examples. I really appreciated it. And we look forward to you joining ExxonMobil and doing great things there.
Great, thanks.
Okay, thanks everybody for joining. We're glad to have you on the line, and thanks for all the really interesting and questions. I feel like
has left the meeting.
The development of this is really spurred on by those who use it and different applications. So we love hearing about those. If you do choose to use the package and want to cite it, I'll just give you a. Let me see if I can pull that up really quickly. there is a page for posting all of the Gecko or APMonitor publications, and so I'll just post that as a final link, just with information about what to cite if you do use it in one of your publications. And there we have it as well, the paper, the open access paper, if you're interested in that. So thanks for joining, and we'll have some additional webinars. If you have any ideas for a webinar that you'd like to present, or know somebody else that would be a good webinar speaker, we'd love to hear that, and then we'll get that onto the list of webinars for the next couple of months. So feel free to email me if you'd like. I'll just put my email in the chat window as well. And feel free to reach out if you have any suggestions or have any other follow-up questions. Again, Logan will post a copy of the presentation to the GitHub repository, and we'll follow up with us if you have any other things you'd like to ask. Okay, thanks everybody for joining.